Okay, good afternoon, everyone. So we have a busy program today because we're finally getting into something that's a little bit more useful. So I want to show off two applications of this technology. So there are two situations where Scala is not just a programming language itself, but a vehicle to deliver the kind of stuff that one likes to do in practice. So I'll start out with what's probably the most useful of it, and that's the processing of XML. Now, when Scala was first developed a few years ago, XML was a hot thing, and everyone had to do XML. These days, maybe not quite so much, but still, it's useful in many situations. And so the Scala people boldly went ahead and put XML right into the language. So in the language, you can put in XML literals. So what you see here is, what's actual XML, the head element, it's the closing of it inside a title element, and then some text. And then you can write it and you can assign it to a variable. And so this thing has type scala.xml.element for an XML element. An element is something that's enclosed in tags. You're going to have sequences of these things. So here I have a couple of, now I'm doing all of these examples with HTML because I figure that's what you're most familiar with. So here I have a couple of elements in a sequence, like you might have inside an HTML list. And that's fine too. That's a valid literal. And that's what's called a node sequence. Just as an amusing thing, in case you ever want to try this with your own programming language, it sounded like such a bright idea to put in like the angle, just the XML angle brackets right there. But of course, the angle brackets are also used elsewhere. And so if you have a construct like this, where you have x less than y, this actually confuses the Scala parser. It doesn't think this means that x is less than y. It thinks that the angle bracket y is the start of an XML element. And you'll get an error message. So you have it works if you have either no space here or if you have two spaces here. Then the parser is OK. So that's a little bit of a wrinkle. And so in the future, they've decided that maybe this is not actually such a good idea to give preference to one particular thing, namely XML, in a general purpose programming language. And they're going to be using strings. You've seen the strings that start with an S for where you can put in variables and they get interpreted. And they're going to make us put XML quotes around it. But right now, we still, if you use XML, you enjoy that luxury of having it as a first-class citizen in this language. So that's a bit of technicalities. So a node is, everything is a node. I have a picture here where you can see that everything is a node, and then you have some class hierarchy of the elements here. Then you have text. And so if you know XML, you'll know that there are things like entity references and comments that are not all that commonly used. But so generally, we care about nodes. Node could be text. It could be an element. That's really how we're going to be looking at it for today. If you have an element, then what normally one calls the tag name is called the label, so e.label. For example, if you have an image element, then e.label would be img. You get the sequence of children of an element by calling e.child. Why the singular? Because that's what they used in XPath. It's the child axis that contains all of the children. Now here's a bit of a weird thing, that when you look at the inheritance diagram here, you see that there is a node sequence. And a node sequence is something that you want to have. It's because it happens all the time. You have some sequence of XML nodes. Like I say, the children of something are such a node sequence. And now they made a node sequence, a subclass of sequence of node. That makes some sense because there's some operations, some matching operations that make sense on node sequences. And then they did something bizarre. They made node extend node sequence. And so don't try that at home, because it actually creates more problems than it solved. Their brilliant idea was that they say, well, that way all of the things that make sense on a node sequence also make sense on a single node, and they thought it was a good idea. It wasn't. But that's another reason, by the way, where it's tough to build in first-class support for this kind of a data type into a programming language. Because think about, particularly with a language like Scala, how does a support like this get in? So who wrote the XML support for Scala? It was a graduate student as part of his PhD thesis. And he was a very good graduate student, so he really did a great job, but he necessarily had a limited view from his own experience of which parts of XML were more valuable than others. It's a very complex standard, actually, surprisingly for something that should be so simple. And so he made some missteps there. And now it's in the language. It's not a library. It's easy enough to throw out a library, but because the syntax is baked into the language, it's difficult to swap it out. And so that's another reason why we're not going to see this package there forever. In a future version of Scala, they're going to make it more into a library, so it would be easy to have a different version of it. Anyway, so there are some of these strangenesses, and you're going to run into that in the lab that you just have to remember. You could, in theory, gather things when you build up new XML. Here's one reasonable way of doing it. You can make what's called a node buffer. You then add items to it, and then it automatically gets converted to a node sequence when you need it. And after it's done, don't mutate it. So in general, we want to have immutable constructions, and it's best to make everything immutable. But once in a while, it's just easier to build it up in this fashion. Temporarily, it's okay to mutate, then just leave it immutable afterwards. So this way, you've seen how to, if you have already XML read in, and you'll see in a minute how to read it in, you can look at the children and the grandchildren. And the grandchildren, you can traverse the XML tree. You can build up new XML in this way. There's a way of looking at attributes. Attributes are the things, so when here, for example, I have an image tag. So img is the label of the element, and the thing inside here is an attribute, and this thing here is another attribute. So you often need to process those attributes, and they're kind of like a map-like thing, but not quite. So when you call attributes, and then in parentheses you put the attribute what you want, you get the attribute out as a node sequence. So really what you would like to have it at is as a string. Like in this example here, we would just like to have the string with logo.jpg. In this case, we would like to have the string, yeah, and that's where it gets complicated, because when you look at the string carefully, notice this thing here. This is what's called an entity. This is how one, from an HTML point of view, we say, of course, that means an E with an acute accent. But that's not how it's represented in XML. This is some opaque thing that through some other process that's defined by some subpart of the standard then gets looked up somewhere. And so when you look it up, you actually get a sequence of 3 nodes. You get this text, this entity, and more text. So if you don't care about that subtlety, then you can, and that's what we'll do for our exercises, you call this toAttrMap method, and then you just get a regular map, and you're good to go. All right, so you can look into these attributes with some subtlety. But now it starts getting interesting when you look at this really nifty trick on how to do embedded expressions. So this is probably, in a way, this is something that, frankly, I had never seen before, and it's very powerful. So what you can do is you write some XML, then you write an opening brace, and inside there you put some Scala code, and it gets interpreted, or it gets executed at, not interpreted, it gets executed at runtime, and its result gets spliced into the XML. So here I might have a list of items, and now I turn that into an XML bulleted, an HTML bulleted list, where I see the first item and the second item. So very nice, very easy to do, much, much easier than if you had to write the equivalent code in some other language. Because in another language, not only would you have to worry about the building up this thing through a loop, maybe, but you would also have to worry about encoding stuff. So item 0 here, for example, might contain text. And as you know, when you inject text into HTML, you have to escape angle brackets, for example. It's done automatically for you. You don't have to worry about it. What if this thing contains other sub-elements? They just get spliced in the normal way. So you don't worry about it at all. Well, there's a couple of cautions in here, and I'm not going to lecture about them. My attorney made me put them in here. We might run into one or two of these things in the lab. So more interestingly than that, check out this statement over here. So we have a UL, and inside it, we have some Scala code. Now this Scala code here, we have items, which is a list of something. And now we're mapping each of the items into more XML. So we have XML that contains Scala, that contains XML, that contains Scala. But it's actually, it's super useful. What this thing does is it builds a UL that contains what? It contains a bunch of allies, each of which contains whatever was the list element. So this thing builds up a bulleted list of all of the elements that are in this items thing. And it's pretty easy. It's pretty natural. It'll even be more natural with the for comprehension syntax that you're going to be seeing in 2 weeks after the break. So, by the way, it could happen that you actually wanted to have these symbols inside XML. In that case, you have to double them. What if you wanted to build up expressions where the attributes are variable? It's the same syntax. So here I have an image element, I have the source attribute, and I want to put in some arbitrary file name in here. And I call some Scala code that does that, and I enclose it in the braces. In this case, you just have to be careful not to use quotes. For some reason, you just don't. That's the way it goes.
You could just put an S before the quotes.
Yes, you could. No, actually, no, that's not true, because what would happen if you did? Then it would always be a string. Now, for an attribute, you might say you almost always want a string, so it's a minor thing, but it would be subtly different. Okay, so let's put this to work here. So what does this thing do? So what it actually produces, clearly it produces a table. And then for each element from 1 to 10, it produces a TR. And inside these TRs, for each of these 1 to 10, it produces a TD. And then it puts in some multiplication table here. So there's a /TD here, another TD, and then I guess a 2 and then it closes this TR, makes another TR, and so on. So that's what it does. So which of these four is the right answer? So commit yourself to an answer. So we have a bunch of B's. I think B wins the popular contest, but a couple of D's and an A. And so when I had forgotten the answer, and I was almost going to vote for D, but what's wrong about D? No. So this is where maybe I should have actually gone into this detail. They're not text nodes. They're atoms of ints. So yeah, there are 100 nodes inside there that look to us like text, but for whatever silly reason, they're not put in as text nodes, but they're put in as atoms of int. It's not entirely clear to me why they do that. So when you build up this tree out of Scala elements, they try to turn things into text at the latest possible moment. I suppose that way you could transform them further if you had some interest in it. I've never ever needed to use that feature. But that's the only thing that makes D wrong. Otherwise, it would be true, there would be 100 text nodes sitting in there because it says descendants. It doesn't say the next level. Now, why isn't it A? Why aren't there 100 children? They're nested, right? There's 10 children, and then there is, each of them has 10 children. So there are 100 descendants, but not 100 children. And so that's why it then had to be B. Okay, so you get the idea of how these things are composed, and that with a very small amount of Scala code, you can generate complex things. So putting these things together, as you'll see in an exercise, is quite useful. And I've actually had to do, and this is dear to my heart because I have to do this kind of stuff. I write these textbooks, and with a textbook, when you sell it on the American market, you have to, in the American market, the way textbooks are sold is the professor picks the book, and then all the students have to buy it. So the winning strategy is to give the professor as much goodies as you can. So like they get a test bank with a bunch of multiple choice questions, thousands of them. So they get authored in some way, and then they need to be put into an XML that the learning management system can handle, and each of them has their own XML. And so the programs, the way that I generate those XMLs is actually with Scala, with just this kind of thing. I read it in from somewhere, and then it gets transformed into the different kind of XML dialects that each test bank system needs for test questions. And the code looks just like that. It'll just iterate through all of the various questions. You'll see it in the exercises, how one does stuff like that. It really is very useful. So the other thing that's really nifty is oftentimes when you work with XML, you get a bunch of XML from somewhere, and you have to take it apart, find things in it, and then maybe reassemble those later, but maybe just report on what you found inside it. So normally the way one does something like that is with a thing called XPath. And so if you've ever used XPath, it's pretty powerful. You make these XPath expressions that say what it is that you want to search, and you get stuff out of there. But then what do you do with them? XPath is only a query language. It's not a programming language. And so then you still have to get them in your host programming language. Particularly if you do this in Java, then you get into the unpleasantness that the XML library in Java is really cumbersome. And then you get this result, and then you have to understand that very cumbersome API. So here, they didn't give us quite XPath, but they said we're going to build enough XPath right into the language that you don't even miss it. So they overloaded, they defined these operators. Oops. Like in XPath, the operators are called slash to find something one level and slash to go multiple levels. They couldn't use the forward slash in Scala because that's a comment. So they turned them into backslashes. Yeah?
So because NodeSec is a subtype of sec, you could just do find with and find something that has the text body and return the element?
You could certainly call those elements as those methods, and you can do that, but it's simpler to use these matching operators. For example, if you want to find something that's an arbitrary descendant, then you use the slash.
So the way they did it, they just added methods called backslash
Yes.
into node sec that does the find thing as normal.
Yes, so you can use, yes, exactly. So somewhere when you look at the source code, you'll find there's a method called backslash backslash.
It's
That-
a valid method name that I could use.
Yeah, you can call a method anything you want. Any sequence of symbol characters, even crazy Unicode symbol characters. And so, you know, except for //, which would have been so nice because that's exactly what's used in XPath, but that's a comment. So that's why they had to turn it around. But yes, so, and they could have gone more wild and crazy, but they restrained themselves. They said the only two things that we will overload are the slash and slash slash. Otherwise, they encode things in strings. So here, for example, is how you find any nodes that are in the document, in a body sub-element at one level deep. Then there's some element, and then there's an li. So this way it would match an li, whether it's in a UL or in an OL. And so here they just use a string wildcard. They didn't go beyond that. They're locating something at any depth is very useful. You want to find all of the image elements at stock / image, and that gives you a sequence, a long presumably long sequence, of all of the images stuck one after another. If you want to match an attribute, like I want to know what is the alt attribute of an image, then it's the same syntax again that's taken from XPath, and you have the @ sign here to say this is a search. This should match an attribute and not a sub-element. So if you know XPath, then this is a very familiar notation. And if you don't, it's still very easy to find stuff. So let's try this out. Here I have a bunch of XML. And I now want to find everything in here at some level that is an attribute src. And I want to turn that to text. So which of these four do you think it is? Are you wondering about this slash here?
No, I think it's not that backslash would do comments. You got it.
Oh, I see. No, the comments are exactly the other way around. Yes, that would have been another nice trick question.
I just remembered that fold right uses a backslash as well. Column backslash is fold right.
I'm sorry? Oh, yes, the fold. Yes, yes. All right, so let's see. Would anyone like to give a guess?
I think it could be the empty string.
Okay, so we have a bunch of A's, we have a bunch of D's, and you have a guess? We have an A, and we have a solitary C. Okay, so the A's and D's seem to be equally. So for those of you who said D's, what did you think it is?
So I think that without the text method unification, it would be a node sec containing a node having like hamster and then for.
Yeah.
And this node itself containing two nodes has no text.
Okay.
In XML, we can have text on its own inside the node.
Okay.
So I think it would give us the empty string.
Okay. Actually, so let's just try something out here. Oh, wait. Oh, I can't do that. Okay, I'll withdraw that. I thought I could make one just like that. That's actually not true. When you take a node sequence, let me make a node sequence in another way.
Maybe we can just copy paste the code without the.
Yeah, I don't want to do that because then I give the answer away.
Then we all learn.
We'll do that in just a minute. So here we have a perfectly good node sequence. It's a subclass of that called node buffer, but we don't care. And if I take this thing here and ask for what its text, then it does what it's an XML-ish thing. It'll recursively take the text of everything and put it all together. That's what text does, and you know there's no way that you put it on. And so here elements have no text, but there's text inside here, there's text inside here. It keeps going in there and smashes it all together. So when you read an HTML document and ask for text, you get a concatenation of all the text that's inside there. Not terribly useful for sequence, but that's how it's been since the beginning of time. So it's not that something else anyway. Does anyone else have an interesting something else that they think it is? Who else had D? You guys in the back, you had D. What did you think? So okay. So you okay? That's fair. So could it be B? Totally no way, right? Because this is an element, and there's no way it's going to turn an attribute into an element. Now C is what I kind of thought it was going to be, except of course for the dot text. So let's just see what this part is without the dot text. And that's exactly what it is. So if you don't have the dot text, you get a node sequence because the slash and slash slash always give you node sequence, with which attributes doesn't necessarily make a lot of sense, but they do. And then when you apply the dot text to that, then it smashes them together like this.
How can nodes beyond the text, like it's not a node, it's a string?
Well, let's find out what's inside it. So it's a node. Let's find out what its actual type is. And it actually is a text node.
We have text nodes.
So it has a text node inside it.
It's a leaf then.
Yeah. So that's just what it is. How would I get it? I mean, right now so I had this node sequence here, which sounds like something useful. How would I get it into, say, a list of the strings? The dot text was not very useful; just smashed them all together. What if I want to have a list of the attributes?
Can map.
Yes, then I would do map, and then here I would get a list of them. Okay. So the next thing that's useful is when you have taken some stuff apart and now you want to know what is it that you actually got, you can use pattern matching very nicely. So here I have some node and I want to know what it is. And so I could say, well, maybe I needed to treat images in some special way. So I could say in match case the image here. This matches an image with any attributes and no children. Now an image never has children. It's just something to keep in mind. Like if you wanted to match, say, an li, then you wouldn't do li slash because you never have almost never anyway, have an empty li. In that case, you might want to do something like this. This form here matches an li that has one child, which is pretty normal. But what if inside there was a text and then something in bold and so on? Then you probably wanted to use this form. This matches an li with any number of children. If you wanted to access the children in the ... on the right, which you often do, then you want to give it some name. So if you happen to have just one, then you could put the name like this way. You have, notice carefully this parentheses child, braces child. The thing on the left is a match expression. It's not code. So this child here is the name of a variable, and when the match has succeeded, this variable is bound the single element inside the li, and then you can do something with it. In the more realistic example that you have multiple children, the syntax looks a little funky. You have to say, so you want to match any number of children, and then you have to say children at, and then children gets bound to a list of the children. And then you probably want to loop over it. Here I use a map to do that. And now my lawyers made me put in this sentence that in this case children is not a node sequence. Yes, and so I ran into this at one point when, so you match these children here, and then you kind of think everything is a node sequence, and then you later try to use like the / on it, and it doesn't work. Yeah?
Couldn't we put inside the braces node sec?
It wouldn't match.
It wouldn't match.
No.
It's
For-
a case class.
It is not a case class. No, it's not. And which is what you just saw, because when I tried to do it here, I didn't get it to work. Yeah. Yeah. So now the key insight, though, is that what you often want to do, at least what I often need to do in life, is I get some XML from one source, and then I need to transform it into something different. And as an example, the Scala book that I wrote, this is exactly what happened, that it was written in XHTML, and then they needed some transformations in it for typesetting. I have a Java book that at one time was written in one XML dialect, then the publisher changed his mind and said, now we're going to do all of the XML different and better. And so I hired a graduate student who wrote a Scala program over a period of a few days that transformed 2,000 pages of XML from one dialect to another with 0 flaws. So that's one of the promises of XML, that you can do this kind of stuff. But the way that it's usually done is, if you've ever had an XML course, they sell you on something called XSLT. Has anyone seen XSLT? So in XSLT, you can, yeah, I see nervous laughter there. You can do this. You can read in XML and then transform it. But I have never been able to do anything with it because the syntax is so weird and it's so fiendishly forbidding. I mean, it's worse than eating soup with a fork. Whereas when you do this in Scala, it's generally pretty easy. So I have done this on a bunch of different projects where this need arose to take large amounts of XML and transcode them. And I've always found that it's really quite pleasant because you try something out and you make a small sample in the worksheet or in the REPL, and so you learn how to do these translations. You smash it all together, and it really just works. So here's how you do the transformation. It's a little funky, but so you have a big old tree, and now you want to make some change in it. Let's say I wanted, for whatever reason, I wanted to change in my slides, which are written actually in XHTML. I wanted to number all of these things here instead of having them bullets. And I wanted to do that for all elements that are ULs and change them all to OL. So here's how you do it. You have to make what's called a rewrite rule, and you override this transform method. It gets a node, and it needs to decide whether or not to transform the node n, or really it assumes it transforms them all. So if n matches, and now we need to figure out what do we want to match. We want to match things that are ULs containing arbitrary stuff in them. And I'll bind this thing to E so that I can use the name. Because over here n is a node, and I want it as an element so that I can call some elements methods on it. But apparently that didn't work because I have an as element, as instance off here. I don't quite know why I have that. This might be some meanness somewhere. And now there's a copy method that lets you take a node, and remember, we don't edit nodes because it's all immutable. So copy makes a new node that keeps everything, the children, the attributes, everything exactly the way that it was, except for what we tell it to change. If you want to change the label, then you say, give the copy this label.
Is that by name parameter or something?
No, that is a it is a by name parameter is the one with the arrow that's for call by name. This is a named parameter. That's what they call it, a named parameter. Yeah. So that's some Scala syntax that I think we've seen a couple of examples here or there of that.
We only used to define methods, but never when we call them.
We've never seen this. Okay, maybe I'll ask. Maybe in the next lecture we can get a couple examples in like that. So the syntax is that you can have default parameters. For each of the arguments, you can say, if it's not specified, I want this default. And then if you want to skip all the defaults but override one of them, then you use this syntax. But that's a good point. That would be nice to see that on the declaration side.
Also, it looks like Java, because I would think that in the Scala way, we will rewrite rule and pass it a function as a parameter. And here we do
Yes. That is totally true. I didn't come up with this. So that was Burak, the graduate student. And in fact, one time I independently rediscovered this technique, and I did exactly what you did. But this is the way it's in the standard library. You can add as many of these rules as you like. So typically I would have, if it's a simple rewrite like this, I might have one or two. But I've had a situation where I wanted to rewrite absolutely everything, and I had a long list of these rules. Or sometimes you can put them all into one with just lots and lots of cases, depending on what how much rewriting is involved. So the general strategy is you just say what those rewrite rules are. You run the transformer through it. It's maybe not the most efficient thing, but if you have a few thousand pages of a book or something, you don't care how long it takes. And so this copy thing is your friend, and you can do any number of things when you do copy. For example, let's say you want to change the child axis, then say you wanted to append something else to every list. I don't know why, but then you would say, okay, take the original children and append something else to it. You'll see a practical application of this in the lab. If you need to change attributes, there is a wildly inconsistent way of doing it that I don't think we're going to need, so I'm just going to leave it on the slide, and if you need it, you can look it up. Finally, loading and saving. This is a bit of a cause for unhappiness, but in practice, but I don't think you're going to notice it for the labs and the exercises. There's at least 3 different ways of reading in files. So you can use the standard Sax parser that comes with Java, and that's the call that you use. You can use a different parser that someone wrote because they needed to preserve white space for some reason. Oh yes, and the reason was that they were reading in HTML, and it had things like scripts in it, JavaScript, and so they wanted to edit it and then write it out again, and so they needed to preserve that, and so they wrote themselves a different parser for that purpose. And that parser has some minor weirdnesses that hopefully we don't really care about. And then someone wrote yet another parser that just works for XHTML, and they were upset about, I think, entity handling, and they resolve entities. So this is something where the standard library just randomly accreted a couple of the things. Whoever yelled most loudly got it put in the standard library. And then at one point they stopped, and so now we have 3 half-assed parsers in there. And there are other, that's where really, where it shows that, this is not something that should be, that the language should really focus on. They should have made it in such a way that this is an add-on thing, and it'll go in that direction soon enough. There are now any number of alternative XML handling packages for Scala. They just have the difficulty that they don't interact nicely with the native syntax. And so for the normal kind of work, one tries to use one of these first. Then to save, again, there are 2 different ways of doing it. There's an XML.save and an XML.write. And on a good day, I could tell you what the difference between them is. That just have different and inconsistent options, and one just has to figure out which one is necessary for some particular context. What always surprises me when I end up doing this stuff is, you'd think XML is the simplest thing in the world, right? You have angle brackets, and you have attributes, and you have nesting, and I mean, how hard can the darn thing be? But in practice, there's all of these little wrinkles, like comments, right? You think, comments can just be thrown away maybe, or maybe they should just be kept verbatim or something. And that people who do different things. Or these entities, why can't they just be preserved? And there are reasons why the XML standard actually forbids you from doing reasonable things at times. The same thing with white space. Sometimes it's significant, sometimes it isn't. And so in practice, there are more wrinkles to this than meets the eye. And you'll run into this when you use one of these in practice. But there's usually some way around it. It just is amazing how complex this stuff is. That's why I think Peyton Jones said that the problem that XML is trying to solve is not very hard. And XML doesn't solve it very well. That is certainly true, but we are stuck with it. All right, so let's do some interesting piece of work here. So the first one, I think is like a cheap thrill, but it's simple, and it's actually something that I use quite a bit. So when I first learned this, I said, what do I want to do? What do I need to do all the time? And one of the things that I need to do all the time is I needed to like find out what images I have in my slides. And so I just want to find out what are all of the IMG tags in an HTML document. And it's a few lines of code. So you'll see that. And so I think that's an enjoyable little program that does something that's genuinely useful. The next thing here is, and this is this quiz generation thing. This is something that I actually had to do for an ebook. So in that ebook, we have this little element here that does interactive quizzing. It's going to look weird when I do it here because when I click, the slide advances as well. So imagine that didn't happen. So I'm going to click on this thing, and then the JavaScript in this ebook element says, no, that wasn't the right answer. But forget that I had to go back and forth. I don't have to do it in the ebook. And it says this one is the right answer. And so the questions that we had thousands of them, literally thousands, in this format. It's called the Aiken format for quizzes. And they had to be turned into something electronic. And so you're going to do exactly that for one question. Once you can do it for one, you can do it for 1,000. And the third one is an example of transforming. That's also a very realistic example. When you think about what you do in HTML with headings, so you have a heading and you have a subheading and another subheading, but it's actually not very logical because you're thinking of structured text where you properly nest things. So you would think that this contents here, that belongs to the second part, and it should somehow be all nested in a thing. Some people conscientiously use a div for this kind of stuff. And in HTML5, they said, you guys should really do the right thing. One should really use the section tag and semantically denote what is a section. That way, a reader might be able to collapse them automatically, stuff like that, instead of having to somehow try to guess or divine the structure would be right in the document. So now you suppose that you have a website with a few 100,000 web pages like this, and you're told, we should really be the right thing and do this in HTML5. How would you do something like that? And that turns out not to be terrifically difficult in Scala. Maybe a little longer than we can actually do in the lab. We'll see whether we have enough time for it or not. But we'll give it a good try. So let's get going with this, and I will walk around and see how you guys are doing.